is now being recorded. As yesterday we had completed mass analyzers, which was a part of actually mass spectrometry. In the case of mass spectrometry, there are two main components of a mass spectrometer. One is the mass analyzer, which is the heart of the mass spectrometer, because all qualitative and quantitative determination with the mass spectrometer depends on the mass analyzer. And second important device or component for a mass spectrometer is the ionizing devices. Whether it is chemical ionization or whether it is electron ionization, that ionization process is important, because the ionization process is going to produce ions which can be analyzed. Now, before I start, I had completely forgotten about the quiz and the questions that I had asked. I'm providing answers as well as some of the observations I think which I should share. The first question was about the mass not being determined, and what to determine is m by z. The answer that was expected was that when you are using a mass spectrometer, you are able to determine anything for a given species, provided it carries charge. If it doesn't carry charge, then you would not be in a position to determine anything with a mass spectrometer. So naturally, what you get is m by z, because charge being the navigator, charge being important in making the detection and the determination in the mass spectrometer possible. So automatically the equations used in the because of the magnetic and the electric field applied, those equations involve m and z both, because z is mainly responsible for the detection and determination, and that's why what you get is m by z and not m. And because we assume that z is 1, in most of the cases it is the situation, m by z can be equated to m. That should have been the answer. The reason why it is m by z, most of the people have written that because z is 1, m by z is equal to m. That is fine. That is afterwards. Why it becomes m by z is because it is the charge species which are detected and determined in mass spectrometry. And therefore the equations give you m by z and not m alone. Then the second question, many of the students have not understood. I purposely wrote T1 plus T2 and T1 dash T2. The reason for that was T1 dash T2 always represents a hyphenated method, where I said that T1 and T2 are the two techniques which are used. So T1 dash T2 will always represent what you call as a hyphenated technique, and T1 plus T2 will represent use of two techniques, one after the other, for the same sample. And that was the difference which I expected. Unfortunately, everybody has written T1 plus T2. Most of them, not everybody, I'm sorry. Most of you have written T1 plus T2 as the hyphenated technique. The very way you represent a hyphenated technique is with a hyphen or a dash. So T1 dash T2 will represent the hyphenated technique, and T1 plus T2 will represent use of the two techniques, T1 and T2, one after the other. Then the third point was the third question about the AS and IFTI or IR, what was asked, and that everybody has answered no, because both are optical methods, so they cannot be converted or combined together to form the hyphenated method. Then PIC and total ion chromatogram and single ion chromatogram is a monitoring system, that everybody has answered correctly. And the function of the mass analyzer, that was the last point, also most of you have written correctly. My observation is, when you are given a quiz, you are supposed to do it on your own and answer it on your own. That is what is expected from you. And what I observed was, from the language, from the sentences which were there in the answer, that there are 3 or 4 or 5 groups, and then it was one person writing the answers and others simply copying whatever that person has written. You could make out because even the commas and verbs and sentences to sentences, everything was same. It obviously means that it has not been a solving exercise. It has been a copying exercise. Somebody writes and the remaining 4 or 5 people will just copy what that person has written. The loss is yours, not mine, because you are copying something which somebody else has written. Whether you have followed what he or she has written or not, I don't know. So I will never come to know whether you understood the given subject or the given topic properly or not, because you are not writing things on your own. You are simply following somebody, copying somebody who has written the answers. And your explicit faith that whatever he or she has written is correct, and that's why it could be easily copied and written down as the answer. As I said, it's going to be, the loss is going to be yours, as you will not be able to write things on your own if you follow this practice. And I said this in the end because I did observe that there were about 3 or 4 groups where the students, one person must have done the answers and all others copied, because word to word, sentence to sentence, the answer was exactly the same. So please remember that when a quiz is given, it is not a copying exercise. It is something which you have to think on your own and answer. Since it is an online process and not done in a class, the lecturer or the teacher does not have any control over it. And obviously, he or she has to just infer from whatever has been submitted. And basic idea of this is to make you understand, make you think, and then give the answers. And that purpose, the very purpose for which the quiz is given, that very purpose will get defeated if you follow this type of practice, which either shows your laziness or it shows your reluctance to do something on your own, or it shows your indifference to whatever being done in the class, because you don't want to follow that and you want the answers. Fine, you want the quiz to be submitted. Okay, fine, this is where it is being done. That type of attitude will take you nowhere. That's the only thing I can say about it. And as I said, if it was done in the class, I would come to know who has written, who has not written. Since it is an online, since it is given as a quiz, and everybody is expected to come up with the answers on their own writing or submitting, this type of copying business may save your time, but it will take you nowhere, because you will not be in a position to think on your own, formulate your own answers, and you will be always dependent on somebody else to provide you with the answers, which you can copy and just submit as the submission process begins. So please remember this point henceforth. You may have the same point as the person who has written the answer as, but then try to formulate it in your own words. Try to present it in the way you want it, not as somebody else has done. The ultimate answer or ultimate outcome of what he or she has written and what you are going to write may be the same, but it should be in your own words. You are formulating your own answers and not copying a ready-made answer passed on to you from somebody else, maybe your friend or somebody else. So please bear this point in mind, because ultimately all this is being done for your sake, for you to understand. And if you are not taking that in the proper spirit or the proper way in which it should be taken, then as I said, we are not going to be at any loss at all, because we are not the persons who are going to think and then formulate the answers. You are supposed to do that. And if you don't do it, you will be at a loss. Okay, so that's as far as the quiz is concerned. Just a minute. Why it is going on one side? The screen should be at the center. Okay. So we'll take up the interfaces in LCMS, and interfaces in LCMS are functionally very important. There are 2 points about the interface. It is taking the solute from the LC to the MS. So you should know what type of analytes are analyzed in an LC and how they will get transferred to an MS. When is liquid chromatography used? Liquid chromatography is usually preferred when the solute or the analyte is non-volatile. It cannot be vaporized, or if it is vaporized, it gets fragmented, it gets decomposed. And in such cases, you will go for LC instead of GC, because GC is usually applied for those compounds which can be easily vaporized, which will not decompose, and they will be thermally stable, not thermally labile compounds. If they are thermally stable compounds, easily vaporizable, then GC will be applied. LC is applied only in those cases where the solute is non-volatile. Either it is non-volatile, that means it does not readily get vaporized under the temperature conditions of the GC, or the solute may undergo thermal degradation before it gets vaporized. It is a thermally labile compound, unstable compound temperature-wise. Then you go for LC. The third reason for going for LC is a better resolution is possible in LC, because both the stationary phase and the mobile phase in an LC, both are liquids and both have the property of solubility, and therefore better separation can be achieved because both the phases are making the solute, the analyte, the components dissolve in them. Whereas in case of a GC, you will find that it is only the stationary phase which will try to dissolve, whereas the mobile phase, which is the carrier gas, it will simply carry the solute along with itself. So these are the three basic points about when you go or opt for an LC. Another important feature when you opt for an LC will be for biomolecules. We'll come to that later on. That most of the biomolecules are large molecular weight compounds, and obviously it won't be possible for them to be entrusted with the GC for the analysis because they may not be get vaporized so easily. So these are the situations in which a liquid chromatography is utilized. Second important point is the concentration range over which GC and an LC works. Even though gas chromatograph also works, is fairly sensitive, has got a lower concentration range. In a case of an LC, you can always go to a concentration level which is lower than that in GC, which is possible because LC is a more sensitive technique as compared to GC. So you can go to a lower concentration level determination in case of an LC. Now, all these points will have to be taken into account when we consider the transformation of the solute or transporting of the solute from the LC to MS. Now, when you want to do it, you should also be aware of what exactly are the conditions in an LC operation and what exactly are the conditions in a MS operation. You know that all liquid chromatographs, they work at room temperature, ambient temperatures, correct? Both involve liquid mobile phase and liquid stationary phase. So if you have a liquid stationary phase and a liquid mobile phase, so the eluate that comes out of the LC will contain the liquid mobile phase along with the analyte, along with the component, along with the solutes. And that phase is now to be transferred to the mass spectrometry. So basically, when you take up the analyte or the solute coming out of an LC, it will contain the solvent along with a small quantity of the analyte or the solute coming out. As I said, in case of an LC, the concentration level of operation may be lower than that one can opt for a gas chromatography. So this is to be transferred into a mass spectrometer. What exactly the interface is supposed to do? What comes out as a eluate will be a large quantity of the solvent, which is the mobile phase, and a small amount of the solute, which is coming out from the LC column after the elution. And this particular mixture of the mobile phase and the solute is to be separated by the interface in such a way that most of the mobile phase, the solvent, we can say, is removed from the mixture and only the solute is transported into the mass spectrometer. So that is the first job of the separator or the interface, which is going to be used between the liquid chromatography and mass spectrometry. You have a large quantity of mobile phase coming out along with the analyte, along with the solute. And we don't want that mobile phase to go into the mass spectrometer. So the first task of the interface that you're going to use in LCMS is removal of the mobile phase, which is in very large amount as compared to the actual amount of the analyte or the solute that is present in the mobile phase. Now, mobile, in the case of a DC or in case of a gas chromatography, it was easy because it was a gas. And if you remember when we discussed interfaces in gas chromatography, we said that in most of the situations, the carrier gas is of lighter weight as compared to the solute, because you are using carrier gases like hydrogen or helium or nitrogen or carbon dioxide, which are having a mass lighter than that of the solute molecules. And therefore, separation of the gaseous component from the carrier gas was quite easy because you had the carrier gas much lighter in weight and mass as compared to the solute. Now, when you take up an LC, you will find that the situation is different. You are having a solvent, and along with that solvent, you will have the solute dissolved in it and coming out of the LC column. So you want to remove the solvent, and you will have to take the solute and ionize it to transport it to allow its entry into the mass spectrometer. Now, how will you remove the solvent? You can remove the solvent by converting it into the vapor. That is the only possible way you can do it. By techniques, by methods, you try to see to it that the mobile phase, which is the solvent used in the LC, that mobile phase is removed in the form of a vapor. And any technique which can offer vaporization of the solvent will be preferred in the interface. So the first task of the interface is to remove the solvent so that there is only solute remaining. Solute is dissolved in the solvent, and you try to remove the solvent by any method, by hook or crook, if you can say. You want to remove the solvent, and then the solute can be transported to the mass spectrometer. So the first task of an interface in LCMS is removal of the solvent, and which is brought about in most of the cases by vaporization of the solvent. By whatever method you can think about, choose and exploit, use that method for removal of the solvent. Second important point is the solute. Now, if you remove the solvent, fine, desolvation has occurred. Solvent has been removed. The solute was dissolved in the solvent and the solvent has been removed. Desolvation has taken place, and now you are left behind with the solute. Now, this solute is non-volatile. Usually, why do you use LC as I stated right at the beginning? That LC is used for mainly non-volatile solute which cannot be vaporized or converted to the vapor at the temperature operation of the GC. For such solutes, you are going to make use of LC. So the solute that comes out along with the mobile phase, that solute is usually non-volatile. That is one possibility. Second possibility is that it may be thermally labile, thermally unstable, and you just try to vaporize it as it is, directly heating it. It may undergo defragmentation, it may undergo degradation, which is the possibility. So and if you want the mass spectrometer to operate and to accept the solute molecules, the solute molecules will have to be converted to the gaseous phase. So whatever method you make use of, it should ensure you that the solute coming out along with the solvent is transported to the mass spectrometer in the gaseous form. That is the most important criterion for the interface. That the interface should be able to transport the solute into the gaseous phase. So that is the second point. Now what will happen? The solvent is removed, so the solute may go back to the solid state and it may remain in the device which is used for removal of the solvent, and it may get deposited on the walls of the device of the interface which is used for removal of the solvent. So that possibility also has to be considered when you talk about desolvation or when you talk about removal of the solvent from the system. So I want the solute to be converted into a phase where it can be introduced into the mass spectrometer. The liquid droplets that may be formed from the eluate, they cannot be directly allowed to enter the mass spectrometer. Mass spectrometer will not accept it. So you want most of the mobile phase to be removed. That is the first task of the interface. The second task of the interface is that the solute molecules which are present, they should go into the gaseous state so that they can be introduced into the mass spectrometer. Introduction of a liquid in a mass spectrometer or introduction of any other state in the mass spectrometer is not going to help. You want the compound to be converted into the gaseous phase so that it can enter the mass spectrometer. So that is the second point about the interface function, that the interface is able to what you can call as convert the solute molecules into the gaseous phase without decomposition or degradation, because the compound may be thermally labile, it may be thermally unstable. Then what should be the third function for the interface? What should be third function for the interface? Anybody? We have done a lot of mass spectrometry now. So can somebody tell me what should be the third function? We have removed the solvent, fine, which we did not want to go into the mass spectrometer. You have converted the solute into the vapor phase or the gaseous phase, that's what we want, because otherwise the mass spectrometer will not accept it. Then what should be the third function that the interface should serve? Think about, because what you are going to do is, once the solute is in the gaseous phase, that solute is going to be introduced into the mass spectrometer. So what should be the third function of the interface with respect to the solute? Anybody? Think about it. It is a very simple answer.
Regulate the temperature and pressure.
It should be temperature and pressure of the mass spectrometer, you mean to say. Yeah, that is required, definitely. But that is subsidiary. There is something more important than that. What you said is right. It is definitely required. But that is subsidiary. Something more important. Just think about. I am giving you the hint that you are transferring the solute into the mass spectrometer. So what should be done by the interface in addition to these 2 points? Anybody?
Ionization.
Pardon?
Ionization.
Yes, exactly. Because the solute molecule going into the mass spectrometer in the gaseous phase is of no use for us, because the mass spectrometer neglects, cannot work on a neutral species. So if you want the mass spectrometer to undergo all the processes required with respect to the solute, the third important function that the interface must bring about is attaching charges or ionizing the component, the solute or the analyte. Because unless the solute or the component is allowed to acquire charge, it will not be recognized by the mass spectrometer. Mass spectrometer recognizes only charged species or charged particles. And therefore, the solute molecule, if it remains neutral, it will not be detected by the mass spectrometer and the entire process will be of no use. So what you need is the ionization of the solute molecule before it enters into the mass spectrometric system. Is this point clear? So usually there are two possibilities. These are removal of the solvent, that is what we call as desolvation, and conversion of the solute into the vapor phase or the gaseous phase. These are the two main functions of the interface, and at the same time, the interface should be able to ionize the molecule. In some situations, the interface does the one function, that is, it tries to remove the solvent, it tries to convert the solute into the gaseous phase, and then there is an ionizing device which will ionize the molecule so that it can enter into the mass spectrometer in the form of an ion. In some interfaces, the two processes are combined and the interface is able to do everything that is required with respect to the solute before it enters the mass spectrometer. What is required? Desolvation is required. Vaporization of the solute is required. And ionization or attaching ions to the solute is required. And therefore, in some cases, for some interfaces, the interface is devised in such a way that the interface can carry out all these three functions, and then the charged species that you get at the end of it, that charged species will enter the mass spectrometer, that is mainly the mass analyzer. In some instances, especially in the earlier stages of development of the interfaces, you will find that the interface was mainly devised to remove the solvent, desolvation process, and to convert the actual molecule of interest into the gaseous phase, or the solute molecule into the gaseous phase, and then it was subjected to ionization before it went into the mass spectrometer. But you will find that the present day interfaces are such that they will manage these three processes within themselves. These are the basic features that a separator should be able to bring about. The interface should be able to bring about. Apart from that, as somebody else said, there are physical conditions of operation which are different. So the separator is taking care of the main requirements. And what are the main requirements? Desolvation, vaporization, and ionization. So these main requirements the separator has to take care of. But in addition to these main requirements, the separator has to also take care of the actual working conditions in an LC and in an MS. And then try to get the compatibility between the two. For example, you take LC. LC operates at room temperature, whereas mass spectrometer usually operates at a higher temperatures. Not at room, it usually operates at a higher temperature. If you take up an LC, the pressure in an LC is very large. You know that LC pumps are high pressure pumps, and it requires a high pressure to make a liquid phase move over another liquid phase. Because both the phases are liquids, the stationary and the mobile in liquid chromatography. And if you want to run one mobile phase which is liquid over another mobile phase which is also liquid, there are frictional forces, and therefore that particular movement of one liquid over the surface of the other, that movement will occur only at high pressures. So you are at ambient temperature and you are at very high pressure in case of a liquid chromatograph. And when you go to the mass spectrometer, you are at very low pressure, very high vacuum of the order of 10 raised to minus 5 to 10 raised to minus 7 of a torr. That is the usual order of pressure inside mass spectrometer. And the mass spectrometer usually works at what you can call as ambient higher temperature, and the liquid chromatograph works at ambient temperature. So there is a temperature difference. There is a huge pressure difference from several kilopascals. So it is coming down to 10 raised to minus 5 of a torr or 10 raised to minus 7 of a torr. Tremendous pressure difference is there. And the basic feature, as I said, there is a temperature difference as well. So all these conditions are to be modified from the LC to MS, and this will have to be done with the help of the interface. So what exactly is the function of the interface? The interface readies the sample to its entry into the mass spectrometer. So once the sample enters the mass spectrometer, it will undergo the usual processes of fragmentation and then their identification on the basis of residues that you get or on the basis of what has been given out. You can try to characterize the given sample. Correct? So basically, the interface has to see to it that all the requirements are fulfilled with respect to the mass spectrometer, and the analyte is ready, made ready, or dressed properly to allow its entry into the mass spectrometer. Okay. Then there is another point which is of interest, or rather importance, rather than interest, I can say that it is of importance. There are two types of liquid chromatographies that are carried out. One is called as normal, and the other one is called as reverse phase chromatography. One is normal phase chromatography, and other chromatography is what we call as the reverse phase chromatography. So can you tell me what we mean by normal? Normal liquid technique and what is reversed phase liquid chromatographic technique is what I want you to tell me.
Sir, the normal phase is where the stationary phase is non-polar and the stationary phase is polar and the mobile phase is non-polar, while
Which
the
phase?
reverse phase is the other way around.
Normal phase is stationary phase is polar.
Yes.
And the mobile phase is non-polar. Okay, and the reverse phase, it is reverse.
That will be the opposite. So mobile phase will be polar and stationary phase will be non-polar.
Okay, fine. That's correct. Normal phase will have a polar stationary phase and a non-polar mobile phase. The reverse phase chromatography, which is the most often used chromatographic techniques, not the normal phase. What is most often used is the reverse phase chromatography, and it involves the mobile phase as the polar phase and the stationary phase as a non-polar phase. So this point also has to be considered or has to be taken into account when you are talking about an interface and its operation. The reason is, if you take a normal phase chromatography, the composition of the eluate that comes out of the column is going to be totally different from the composition of the eluate that comes out from a reverse phase chromatographic application of a reverse phase chromatographic technique. What happens in the normal phase? In the normal chromatography, the mobile phase is non-polar. So when you get the mobile phase coming out along with the solute, it will mostly have a non-polar solvent along with the solute as the analyte coming out of the LC column. On the other hand, if you take up the reverse phase chromatography, the mobile phase that comes out is going to be polar along with the solute or the component coming out of the column. And when you say it is polar, what exactly you mean? Do you mean that you are using aqueous phase as the mobile phase? When I say that the mobile phase is polar in the reverse phase chromatography, do you mean that the mobile phase is an aqueous phase or the solvent used is water. Is it the case that the solvent used is water? That's what I want to know. Is that the case? Yes or no? The answer is
polar will be mobile phase. It will be aqueous.
Every time it will not be solvent as the water as the mobile phase. It may be polar solvents which can be used. But what is most important point in the reverse phase chromatography, and which the interface has to take into account, is that if you are using a reverse phase chromatographic technique, which is the normal method of operation and separation, in that case, the polar phase may contain a lot of buffers which are used to maintain the constant pH during the separation process. So a lot of buffers are present in the mobile phase, and what comes out is going to be, it can be a mixture of solvents along with the buffer system. Now, the problem that one has to consider or think about is the solvent will readily get vaporized. Fine. Because you are heating, for example, you are heating it, then the solvent will vaporize, the system will get desolvated. But then what happens to the buffers? Buffers are not volatile. Buffers are inorganic salts and acids. So they will not readily get volatilized and as easily the solvent or the mixture of polar solvents which is present in the system along with the buffer. That part may get readily volatilized, but not the buffers. Buffer, what are the buffers made up of? Buffers are made up of the weak acid and their salts, or weak bases and their salts. You are aware of that. And in other words, the buffers will be delivering what you call as a solid material after the desolvation process. Because buffers are inorganic salts and therefore they are not readily vaporizable. They cannot be readily converted into the vapor form. So if you are using buffers which are made up of mainly inorganic salts, then those buffers, particles of them will get deposited on the outer or the inner walls because the buffer is not volatile. It cannot be converted to the vapor phase. So in the solid state, it will remain as it is, wherever it is, after the dissolution process has occurred. And then you are left with a solute and a non-soluble solute in the form of buffers in the given phase. So you will have to take care of this also, that the buffers present may change the entire scenario, because the buffers present may get deposited on the device, on the walls of the device, and may hamper or may obstruct the processes that you want to occur or take place in the interface. So preferably the buffers should or need to be volatile. The ions that compose the buffers, they should be volatile. That may be one of the conditions that we want for the preparation of the buffer. Okay. So I have already talked quite a lot about what the interface in LCMS should do. It should dissolve it should vaporize, and it should ionize. So what I can say is the three basic functions of the interface in LCMS is desolvation, vaporization of the solute, and the conversion to ions or ionization process. Is this clear? Any doubt, any query, any question about this part before we start on to the different types of interfaces that are going to be used? Any query or any question? Feel free to ask. Don't feel embarrassed that this is a simple question or is trivial and then how can it be asked. It is always better to clear your doubts rather than keeping them in your mind. Yes. Okay, then we will go to the actual interfaces which are used in in LCMS system. You will find that there is evolution, changes, modifications, increase in the efficiency over the years with different types of interfaces which are used. We are going to talk about a number of them. What is called as a fast atom bombardment interface, a particle beam interface, a thermospray, an electrospray. These are the interfaces which are generally used. Each interface has got its characteristic properties, characteristic advantages, and characteristic disadvantages. Also, it's not that you have got a perfect not interview. You can say perfect interface fulfilling all the functions, especially when the things are beyond your control. For example, the buffers used. If the buffers used in the system are not volatile, then obviously the interface cannot do anything about it. So there are advancements, and you will find that the current interface systems which are used, they bring about ionization also. So there is no separate ionization device which will produce ions from the vaporized or the gaseous molecule of the solute. Okay. So let's take the first case. The interface plays very important role. In the case of an LC, the eluate that comes out is at very high pressure, and the mass spectrometer is of the order of 10 raised to minus 7 of a torr. So what has been considered is the basic difference in the physical conditions. LC works under very high pressure, and mass spectrometer works under vacuum, almost a very high rigid vacuum. Secondly, the solute that comes out is not in the gaseous phase. So solute may get deposited after removal or desolvation. It is something which, if you can identify the process, it is something similar to what happens in atomic absorption spectroscopy. Solvent is removed, then the solute is converted to the gaseous state. The solute undergoes dissociation, and then the atoms are produced. So it is desolvation followed by sublimation, followed by dissociation or atomization. That's what happens in case of atomic absorption. So similar type of situation is over here. Desolvation definitely has to take place. The conversion of the solute into the vapor phase has to occur, and there may or may not be fragmentation, but there has to be ionization. So these the last two steps are different, but basically the first two steps are same between this and what we call as the atomic absorption spectroscopy. The solvent is removed and the solute is sublimed. The same thing happens over here in LC also. The solvent has to be removed and the solute has to be sublimed. Secondly, the solutes that comes out is not in the gaseous state. Thirdly, the solvent used as the mobile phase has to be removed so that it does not enter the mass spectrometer. So solvent in any form, vapor form entry of the solvent is very easily possible because solvents are usually volatile solvents which are used for dissolving the solute. So the possibility of the solvent vapors to go into the mass spectrometer along with the regular molecule has to be eliminated. Otherwise, the fragmentation of the solvent will occur, and you will get, along with that, you will also get the fragmented solvent molecules in the mass spectrum. Thirdly, the solvent used as the mobile phase has to be removed so that it does not enter the mass spectrometer. The solute that comes out is not in the gaseous state that we already discussed. The basic task for the interface is to remove the solvent and convert the solute to the gaseous phase. Correct? The second important point is about the volumes. You know very well that when a liquid gets converted to the vapor, the volume of the vapor is very high as compared to the volume of the liquid. A simple example which we always give is if you take 1 ml of water, you know how small 1 milliliter of water is. But if you vaporize that and convert it into steam at the same temperature, not even higher temperature, at the same temperature, then the steam formed has a volume of about 1700 ml. So 1 ml can generate steam equivalent to a volume of 1700 ml. So that is another point which has to be considered, that you are going to remove the solvent fine. But in the process of that, when the solvent is getting desolvated, the sample is going to get rid of its solvent. The solvent volume is going to increase considerably when it goes to the gaseous phase. So that point has to be considered or taken into account when you take the device for the separation purposes of the separators that you are using. The next important point, I think, I don't know whether I emphasized this earlier or not, is there is a huge amount of solvent and a very small quantity of the solute. The solute that comes out along with the solvent will be in very small amount, because if you are able to remember the GC and the LC, you will know that an LC functions at a lower concentration level compared to the GC. So the amount of the solute that comes out of the column of LC is going to be very small compared to the volume of the mobile phase that you are going to have. The entire gaseous volume can't be admitted to the mass spectrometer, as it can take up only at the rate of 1 ml per minute. So, and the last point is that the LC works under ambient temperature conditions, whereas a mass spectrometer usually works at a higher temperature or at an elevated temperature. It's not specifically that the mass spectrometer works at elevated temperature. It has to. Can anybody tell me why the mass spectrometer has to work at a higher temperature? The LC works at a lower ambient temperature, whereas the mass spectrometer works at a higher temperature. What is the reason in both the cases? Why you can work for an LC with ambient temperature, and why you have to work for a mass spectrometer with a higher temperature? Both the points I want as the answers. You should be able to think an answer. What is the reason for LC to operate under ambient or the room temperature conditions, and what is the reason for the mass spectrometer to operate at elevated temperatures? Why should LC operate at ambient or the room temperature? Yes?
Sir, because we are analyzing the liquid, we can't allow the liquid to convert it into the gaseous phase. So the temperature needs to be ambient in LC.
The reason is you don't want the solvent to vaporize, because that is one point. And second point is the entire separation in an LC is based on solubility differences. And solubility is a factor which gets affected with temperature, mainly the evaporation of the solvent or the volatile phase, which we don't want to occur or take place. And that's why most of the liquid chromatograph work at ambient or the room temperature. Whereas if you take a mass spectrometer, the mass spectrometer has to have the molecules in the gaseous form. You cannot allow liquid droplets of liquid to be formed in the mass spectrometer. That can never be useful. In fact, it will handle or make a harm to the working of the mass spectrometer. And therefore, to ensure that the system remains in the gaseous phase, you have to you make use of a higher temperature so that there is no condensation either of the solvent or the solute to the liquid state. Okay, so that basic difference is there because of this. So what are the interface functions? As I mentioned, convert the solute to the gaseous phase, preferably without its decomposition. That is obviously the first point, that the solute has to go to the vapor phase if a mass spectrometer has to accept it or is going to accept it. Remove the mobile phase. So the volatile solvent or the mobile phase has to be removed. Ionize the solute molecule before entering into the MS system. So before you start the MS system of circulation of solvents, what you have to ensure is, when you take up the removal of the mobile phase, the mobile phase is volatile if it is normal chromatography. In the case of normal chromatography, the mobile phase is non-polar, so it will be volatile. Removal of such a mobile phase will be quite easy. But if you take the reverse phase chromatography, and in most of the cases, reverse phase chromatography is the one that is usually opted for, then in that case, the mobile phase is polar. And what is more important is, apart from the polar solvents that the mobile phase is going to use, you may also have presence of buffers or ionic salts in the mobile phase along with the polar solvent which is used in the mobile phase. And that is the more important point when you talk about the separators or when you talk about the interfaces, that in a polar mobile phase, you encounter ionic salts because buffers are extensively used with a polar mobile phase in what you call as the reverse phase chromatography. So conversion of the solute in the gaseous phase, preferably without decomposition. That is the first point. Then removal of the solvent or the mobile phase, which may be polar or non-polar depending on type of chromatography that you are dealing with. Ionize the solute molecule before entering it into the MS system. Because, as I said, ionization is necessary. Ionization is essential because the mass spectrometer recognizes ionic species, charged species, and it does not recognize neutral species. So neutral bases entering the mass spectrometer are of absolutely no use as far as the analysis is concerned. So ionization should be brought about. If the interface brings about the ionization, then you don't need a separate ionizing system over which the vapor will have to be passed so that it gets converted into ions. If the interface itself is able to perform that function of ionization, then nothing like that. And you will find that most of the interfaces which are used nowadays after the development in the interface technology, most of them are able to perform the function of ionization also. So what enters the mass spectrometer is an ionized species, maybe original molecule or maybe its fragments in the gaseous phase at the point of entry in the mass spectrometer, that is about the mass analyzer. But if the interface does not give you ionization, then you will have to make use of an ionizing source, and the entire vapor phase system that you get coming out of the separator, coming out of the interface, will have to be transferred to an ionizing device so that it brings about ionization, and then only it can enter the LC column. Otherwise, then only it can enter the mass analyzer of the mass spectrometer. Otherwise, if the interface itself is able to bring about the ionization, then the ionized species will enter the mass spectrometer and then it can be directly subjected to the mass analyzer without any further delay. So preference will be given obviously to an interface which is able to bring about all the processes, so that finally what comes out of the interface is a charged species which can be identified, which can be recognized by the mass analyzers in the mass spectrometer. LC is used for those solutes that are not volatile, and hence conversion to the vapor phase becomes important. That I already mentioned earlier. even though different types of interfaces are available for, I think we are starting with thermospray. So basically, what the interface has to function is removal of the solvent, desolvation process, sublimation process for the solute, and preferably the sublimation process should be accompanied by ionization so that a separate ionization may not be required, ionizing device may not be required before the sample enters the mass spectrometer. So what are the different types of interfaces that you are using? Then another very important point is about the type or nature of the molecule that you are talking about. LC-MS system is being used under what condition? That is the first point I wanted to understand. I think I will take up that and then we can stop, go to thermospray in the next class. Basically, when you take up a solute, you apply LC when the solute is non-volatile. It cannot be converted to the gaseous phase. So you go for the LC method of separation, where the two phases are liquid phases are acting as solvents, and distribution of the solute occurs between the two phases. One is mobile phase, another one is the stationary phase. Correct. But when is LCMS used? A mere LC is sufficient for this purpose because you have got a solute which is non-volatile, you have dissolved it in a proper solvent, and a LC is capable of separating the components and even estimating them by means of the detectors. So LC of itself is a really complete sustainable technique. It can take up non-volatile components, separate them, and even analyze them. So basically, when a system, hyphenated system like LCMS is to be used, because normal LC is very capable. It's a versatile technique. It can take care of very low concentrations of the solute particles, correct? And it can bring about the separation, qualitative separation, and quantitative identification, determination also becomes possible. So, why and when LCMS system will have to be used is my question. When LC itself is efficient, a versatile method, a very superb technique which can separate everything under the sun, that is what we usually talked about, that LC is a technique which can separate anything under the sun. So with all these qualifications, why should one go for LCMS is the question. If you are not going for LCMS, then the LC technique is very versatile, very accurate, very sensitive, and all those things. It can be applied. But then why is LCMS needed in that case? Is my question. Can anybody answer? Why do you need LCMS? Because LC itself is sufficient. LC is efficient technique. It can do qualitative analysis, it can do quantitative analysis, it can go to very low concentration level and all those things. Then why should one go for LCMS? Can anybody answer? If you are going for LCMS, it obviously means that it's something which is about the solute is there, which is not, that information is not given or is not possible with only LC itself. Then only one will go for LCMS. Because LC itself is not sufficient to collect and provide the required information, then we'll go for LCMS. So when is this going to happen, or under what situation and what circumstances is it going to happen is my question.
Sir, maybe...
Sir, is the solute?
Yes. Yes, speak out. What were you saying? Please speak.
Kevin, you go first.
Pardon? You understood the question? That LC
Sir,
is a very excellent technique. Right. Yes, somebody is speaking.
Yes,
Please speak.
sir, I was saying that maybe if the compound has two or more structural isomers.
You mean to say structural isomers cannot be separated by LC?
No. In that case, it would be more feasible if we use mass spectrometer. That will give us a better idea of the fragments and all. So,
mass spectrometer does not separate structural isomers. Because if you take the structural isomer, that's the point. It's a good point that you raised. If you have structural isomers, like say geometric isomers or enantiomers or any other type, stereoisomers, they will not be identifiable from a mass spectrometer. Because a mass spectrometer ultimately depends on the M by Z value and the fragmentation process. Unless the structural isomers like the geometric or the steric isomers are able to produce different fragments which can be used to identify the original type of isomer. Otherwise, it is not possible. Detection will be possible with mass spectrometry provided the fragmentation pattern of the two isomers differs, geometrical isomers as well as other type of isomers. If they are able to undergo fragmentation in a different manner, the usual enantiomers or optical isomers, if they undergo fragmentation in a different manner, then only the fragments can be used to identify and ascertain that yes, we are able to separate isomers. Otherwise, it is not possible. Basically, you use LC-MS system where the separation may be brought about, but it may not be possible for characterization or for quantitative determination. In that case, you need an additional technique like MS to do that particular job. And you will find that LC-MS systems are applied mostly in biological sources, in case of biological systems, where you deal with solutes which are of very high or large molecular weights. So in such situations, the LC alone may not be able to characterize. It may be able to separate the molecules, but it may not be able to characterize, identify, or bring about the estimation. So MS system is attached to LC when LC fails to provide the necessary information, and that necessary information is given or provided by the MS attached to LC. So only such situations you will make use of the LC-MS technique. Is this point clear? I think I can stop. Any queries or any questions? Please ask if you have any queries left or any questions left. You'll find that it is monotonous or boring because it is only a description. There is nothing in it to understand as such. It's a description of how the three processes which are there on your screen on the slide, they are brought about by the given interface. That is how you are describing different interfaces which are used in LCMS type of systems. Any query?
Sir?
Yes?
Sir, can there be a case where the sample can have both volatile and non-volatile components?
Volatile and non-volatile? I didn't get the first half of the sentence.
Can there be a sample in which there are both volatile and non-volatile components?
There can be. It depends on the source from which the sample is derived. Correct. It depends on the source.
In that case, how can...
But in that case, because volatile or non-volatile, that problem doesn't arise with LC because LC works on the basis of solubility. So as long as the volatile and non-volatile components are soluble in the stationary and the mobile phase, the separation will be brought about. The conversion to the vapor phase. You are interested in that. When I go from LC to MS or LC-MS system, combined system with an interface, obviously a volatile component will get converted to the gaseous phase very easily or readily. Even for that matter, you won't need an interface. You can just heat the system and it will get converted to the vapor phase. What I want you to understand is even the non-volatile component or non-volatile solute, which may be a part of the sample, that also gets vaporized, converted to the vapor phase. Unless that is done, it will not be able to be analyzed with the mass spectrometry. So whether the solute is volatile or whether the solute is non-volatile, it has to be obtained in the vapor phase before you subject it to mass spectrometry or allow it to enter into the mass spectrometer. And not only in the vapor phase, which has to be charged. Ionization also has to occur. So what you will get is a charged species. So that has to take place for both. For a volatile component, if it is coming out, it will be easier. For non-volatile, it may not be easier. I will give a simple example to illustrate the point. If it is a volatile compound, you pass the eluent that is coming out through a heated capillary. The volatile component will get vaporized. Correct. If you pass the same system through the heated capillary, the non-volatile component will not get vaporized, but the solvent will. So if the system contains mobile phase, volatile solute, and non-volatile solute, the mobile phase and the volatile solute will get vaporized, no doubt, when you are just heating, because that is a normal method of vaporizing a substance. The non-volatile component may not get into the vapor phase at that point. So you have to use techniques or methods where it can be brought into the vapor phase. Is this point clear? So that's how it is done for each of the interfaces. That we will take up next time. Okay? Anything else? Any other problem?